Hello, we're going to cover how to find absolute extrema. So this is the second half of section 14.7. And we have to keep in mind the extreme value theorem that was covered in Calculus 1 because it does extend to multivariate functions. What it says is that as long as our function f is continuous on a closed and bounded set D in R2, all that means is that there's some sort of boundary, a domain that has a boundary, okay? Then we know for sure that our function will attain an absolute maximum and an absolute minimum at some points in the domain, like it has to happen, okay? Now, on the flip side, if we don't have a closed and bounded domain, like we have an unbounded domain, it's infinite, then we have no guarantees about absolute extrema. We don't even have guarantees about local extrema. They may or may not exist. We would just have to do the work to figure out if they do or not. So having a closed and bounded set for the domain of a multivariate function allows us to say, yep, we're going to have extrema, let's find them, okay? But in order to find them, we have to go through our process. The very first thing that we'll have to do is actually draw our domain, okay? So what this says here is first we will still have to find all critical points in the interior of the domain by following the steps for how to find local extrema. So that's what I just did in the previous video, but it really helpful. Draw the domain. And I don't really just mean helpful, I mean it's critical. Like you need to draw your domain. Just do it, okay? Because then next, what we're going to do after we figure out if there are any critical points in the interior of the domain is that we're going to find all the extreme values that are on the boundary of the domain. So oftentimes if you haven't drawn a domain, then you won't actually know what the boundary is and how it's different from the interior. Seeing a picture makes that so much clearer. It'll just save you from getting the wrong answer. So draw a picture, okay? So we're going to find the extreme values of our function on the boundary of the domain as well as at all endpoints. Those are like the vertices or edges, corners of our domain. Critical points can occur on the boundaries of a domain. They could not do so with local extrema, but they absolutely can with absolute extrema. Finally, what we're going to do is find all the values of our function at these critical points. I'll do that as we go through the problems. But we're going to find those values, and then the biggest one is the absolute max, and the smallest one is the absolute min. Pretty simple from there, okay? Steps 1 and 2 are the most time-consuming. Step 3 is when you're done, pretty much, okay? So let's start with an example. Here we are asked to find the absolute maximum and minimum values of f on the set D. We are told that f of xy is equal to x minus y minus xy, and D, that's our domain, okay? It is a closed triangular region with vertices 0, 0, 0, 2, and 4, 0. Okay, first things first, draw the domain. So I'm going to draw the region. Then I'm going to identify the boundary curves. Interior and endpoints. Just so it's like super duper clear for all of us. Okay, so to draw this, it looks like these 3 points are forming a triangle, and they're going to be in the first quadrant. I hesitated because I couldn't get the word octant out of my head. Okay, we're in quadrants right here, so this is x and y, and it looks like we need to go out by 4, up by 2, and then a minimum. Okay, so I have a point at 0, 0. I have a point at 0, 2. I have a point at 4, 0. Now I'm going to connect my dots, and this forms my triangle. Okay, the edges of my triangle, I am making them very solid here to emphasize that those are my boundaries. Those are the things I need to identify, okay? So I'm going to name them, all right? I've got L1, L2, and L3. The big fat circles, those are my endpoints. I'm going to identify those as well, okay? All right, so the boundaries, L1 is defined by, well, let's see, a vertical line going through the y-axis is x equals 0. That's the equation of that line. It is bounded by, so with the y values that are taking place, which y goes from 0 to 2 on L1. L2, so L2 is defined by a line that goes through the x-axis. That would be y equals 0, but only for certain x values, the ones where x is between 0 and 4. L3 is not horizontal or vertical, right? It's a slanted line, and it looks like it has a slope of -2 over +4, which is a -1/2. So y is equal to a -1/2 x, and then the y-intercept value is going to be 2, so +2. And then this equation is true just for the x values between 0 and 4. Okay, now I want my endpoints. And what I want with my endpoints is to evaluate my function at those endpoints. So my endpoints on a triangle are the vertices that we drew. So I'm going to look at f of 0, 0, f of 0, 2, and f of 4, 0. F of 0, 0 in x minus y minus xy just gives me 0. F of 0, 2 gives me 0 minus 2 minus 0, which is -2. F of 4, 0 gives me 4 minus 0 minus 0, which is 4. Okay, so I have three function values, 0, -2, and 4. All right, I've taken care of my endpoints and my drawing, and I know what my boundaries are. I need to go ahead and find my possible interior critical points. So I'm kind of going a little bit out of order with regard to the steps before, because I feel like they need to be broken down even more a little bit. Okay, so we get our drawing, we've labeled everything. Second, we're going to solve f sub x equals 0 and f sub y equals 0 simultaneously for any critical points in the interior. Okay, so we got to figure out what the heck is the interior. Well, the interior is going to be all the stuff inside the triangle. It's any value that shows up inside the triangle, not on the triangle, not on the edges, inside. So only the orange is my interior. If I get a critical point that is not in the interior, I throw it away. Okay? So let's go ahead and find our critical points in the interior. We find f sub x. F sub x is 1 minus y, which is equal to 0. That means y is equal to 1. And f sub y is equal to, looks like -1 minus x equals 0. So x is equal to -1. Okay, so this is one of those situations that I was alluding to earlier when I was talking about local extrema. We're solving simultaneously. I solved two equations and I got a number in each one. I don't like go and just make up another number to go with each one. These are the values of x and y that would make both equations equal 0 simultaneously. So the critical point is -1, 1. Okay, that's it. That's all that it is. And now we go ahead and we find our function value at -1, 1. When I plug this into the function, I get -1 minus 1 minus a -1 times 1. It's a whole lot of ones. So I get a -2 plus 1, which is -1. Okay, that is another critical point and its value. All right. So this kind of takes care of, let's see if we go back up to our steps up here. We basically took care of step 1. We found all the critical points in the interior of the domain, and then my little helpful draw the domain. We've got all that. The next thing we have to do is find all the extrema on the boundary of the domain. And so this is why in the first step, I wrote out what my boundaries are, because now in step 3, I've actually got to take care of those. Okay, so we're going to check all boundaries for critical points. I'm going to start with L1, and L1 is defined by x equals 0, and y is going from 0 to 2. Okay. We're fixing x to be 0. We are on the y-axis. So that what we have to do now is we take our function, f, and we evaluate it at 0y. So everywhere there is an x, we replace it with a 0, and the y's stay there. This is going to give me 0 minus y minus 0, which is -y. Okay, this is a single variable function, which means taking derivatives is even easier now. Okay, so we're going to solve f sub y equals 0. Okay, well that's great. When we go ahead and take or find f sub y, we get f sub y is equal to -1, which is never equal to 0. So what does that mean? Well, it just means that there were no critical points on that boundary. So there are no CPs on L1. Okay, that's L1. Now we go to L2. L2 was defined by, let's see, y equals 0. So now we're on the x-axis where x is going to run from 0 to 4. Okay, we are looking at f of x comma 0. So everywhere there's a y, we're going to replace it with a 0 in our function. That's going to make it be x minus 0 minus 0, which is just x. Okay, now solve f sub x equals 0. Okay, well, when we calculate f sub x, we get that it's 1, which is, again, never equal to 0. And so once again, we have no critical points on L2. Okay? You know, little dissatisfying, but the good thing is it wasn't very much work. Okay? We still have to, you have to do it. You have to show whether you found something or not as a critical point on your boundaries. Okay, we have one last boundary. It is not safe to assume that it will not have critical points. That boundary is the slanted line, so the y equals -1/2 x plus 2. All right, so we're L3. Y is equal to a -1/2 x plus 2, and x is going from 0 to 4. Okay, now here what I'm going to be looking at is f of x comma -1/2 x plus 2. So everywhere there's a y, I'm going to replace it by -1/2 x plus 2. So our function was x minus y, so I'll have minus in parentheses a -1/2 x plus 2. And then minus x times y, which is the -1/2 x plus 2. Now I need to distribute and gather all my like terms. This gives me x plus 1/2 x minus 2 plus 1/2 x squared minus 2x. Okay, so it looks like I have 3 halves x and minus 2x, so that'll be a negative 1/2 x. All right, so in total I have 1/2 x squared minus 1/2 x minus 2. Okay, now I need to solve f sub x equals 0, which means I need to calculate my first partial derivative. So f sub x is equal to 2 times a half is 1, so it'll just be x minus a half equals 0. X is equal to a half. Okay, well, y was equal to a negative 1/2 x, so I'll pop in that 1/2 plus 2, which is going to give me 2 minus a quarter. That's going to be 7/4. Okay. All right, so then the last thing we need is to state that the CP is 1/2 comma 7/4, and then we need the function value f of 1/2 with 7/4. The function again was x minus y minus xy, so I'll get 1/2 minus 7/4 minus 1/2 times 7/4. And when I add that all together, I end up with a negative 17/8. You can just trust me on that for now. Okay, so I'm supposed to go through and look at all my function values. So this will be my 4th step. We're going to compare all function values of critical points. Okay, biggest value equals the absolute max. Smallest value is equal to the absolute min. Okay, so I've got this value I just found down here, the negative 17/8. I had no critical points on L2 and L1. I had one critical point right here, f of negative 1, 1 is equal to negative 1. Okay, and oh, wait a second. I have critical points at the vertices, 0, negative 2, 4. Okay, so all the values put in here together. We have 0, we have negative 2, we have positive 4, we have negative 1, and we have negative 17/8. The biggest of these values, the absolute max, that is occurring at f of 4, 0, because we get back 4. So it's f of 4, 0 is equal to 4. And the absolute min is the negative 17/8. And that was at f of 1/2 with 7/4 is equal to a negative 17/8. Okay, so those are the absolute max and the absolute min for this one problem. We had to do a lot of work for this. You don't get to skimp. You have to do all these steps when you're working with absolute extrema. Okay? All right. The next problem, problem 4, very similar problem, except our region of our domain is different. And so that's why we're doing it, so we can see how do you set up different types of domains and work with them. We're going to do the exact same process though. Okay, so here our function f of xy is xy squared. Our domain is defined by the set of all xy values such that x is positive, y is positive, and x squared plus y squared is less than or equal to 3. So the first two parts of the domain, that tells me quadrant 1. Okay, x and y are positive. The second or the third part of the domain where it says x squared plus y squared is less than or equal to 3, that tells me a quarter circle. And I know it's a quarter circle because it's only in the first octant. It's not in all, first quadrant, not in all the quadrants. Okay, so I need to draw that. With a radius is root 3 in this one. Okay, so first, draw a region and label boundaries. Endpoints, and interior. Okay, so let's draw this. Let me use a different color. All right, I have an XY axis. Square root of 3 is about approximately 1.7. We don't need to have an exact drawing. Approximate is good. So when I draw this at about 1.7, it's going to be almost at 2, but not quite. I'm going to draw my arc, and then I'm going to draw my edges because I know that I need x greater than or equal to 0. That's going to be the y-axis there. I need y greater than or equal to 0. That's bounded by the x-axis there. And then I've got my arc on here. So again, I'm going to label these L1, L2, and then L3 will be for that arc. Okay, now I want to go ahead and define these boundaries. L1 is the y-axis, which is defined by x equals 0. And it looks like y gets to go from 0 to root 3. L2 is very similar. It's the x-axis, which is defined by y equals 0, where x is now going to go between 0 and root 3. L3. Well, we know the equation of a circle is x squared plus y squared is equal to 3, this particular circle, but we just want a quarter circle, and it is where y is positive. So it looks like we could just solve for y in the equation of the circle and then state the domain for x in there. So if I solve for y, then y is equal to the positive square root of 3 minus x squared, and x goes from 0 up to root 3. And that defines my arc. Okay, so those are my boundaries that I'm going to be working with later. Next, I have my endpoints. My endpoints, it looks like I've got the origin. So I need to look at f of 0, 0. If I plug 0 and 0 into xy squared, I just get 0. Then I need f of 0 with the square root of 3. So that's going to be on the y-axis. That's going to be my point right here. And again, with that 0 in there, xy squared is going to give me 0. And then finally, I have f of root 3 with 0. That's going to be that endpoint on the x-axis, and that will also give me 0. So I had 3 endpoints. All 3 of them gave me the same value. Those may or may not be anything when we finish up here. Okay, next thing to do is to solve f sub x equals 0 and f sub y equals 0 simultaneously to find critical points in the interior. And what is the interior? Well, that's this region inside the quarter circle, not on it, but just inside. So if we find a point and it's inside, not on the boundary, not outside, but inside, then we'll keep it. If it's on the boundary or outside, we'll throw it away. Okay? All right, so let's find f sub x. F of xy is xy squared, so f sub x is y squared. Set that equal to 0, we get y is 0. And f sub y is equal to 2xy. Set that equal to 0, and we get x equals 0 or y equals 0. So it looks like either way we look at it, our critical point is 0, 0, and that is not in the interior. That just means I throw it away. I'm not going to consider it. Here's the reason. I'm already considering it as an endpoint, right? Look at my list of endpoints. The origin was one of the edges or the corners of this shape. And so I've already taken care of it. I don't need to do it twice, okay? So I'm done with that step. Third step is to check the boundaries for critical points. All right, L1. Let's get a different color. Okay, L1 was defined by x equals 0 and y was going between 0 and root 3. So I'm going to look at f of 0 comma y. Well, f of xy is xy squared. So if x is 0, then my function is 0. And I'm kind of done there. This has, which has no critical points. Okay, if I take a derivative, I get back 0, but my function was constant to begin with. Okay, so if my function value is constant, like it's always 0, then there is no point that's higher or lower than another on that region. Okay, L2 is going to give us similar results. L2 was defined by y equals 0, and x was going between 0 and root 3. And so here I'm looking at f of x comma 0, which gives me 0. So this is when I can conclude that this has no critical points. I will say it is just a mere coincidence that for the two problems we're working out, we had two lines where there were no critical points. That doesn't always happen. There are no always happens in these sorts of problems. It's like case by case. Okay, we're just happy that it happened. All right, so L3, that's the arc. So this is defined by y equals the square root of 3 minus x squared, and x is going between 0 and root 3. Okay, that means we want to examine f of x comma root 3 minus x squared. Okay, so our function is xy squared, so the x gets to stay there. The y is now going to be replaced with the square root of 3 minus x squared, and then we're going to square it. The square and the square root undo each other, so we're left with x times 3 minus x squared, which is negative x cubed plus 3x. Okay, so now we have a function. It is not 0, so that means we can now go ahead and take its derivative and set it equal to 0 and solve for critical points. So we're going to solve f sub x equals 0 for critical points. F sub x is equal to negative 3x squared plus 3. Set that equal to 0. We get x squared is 1, which means x is equal to plus or minus 1. Now we have to remember our domain. Our domain has us in the first quadrant, which means x equals negative 1 is not one of the solutions. So only choose x equals 1 and y equals the square root of 3 minus 1, which is the square root of 2. Okay, that will be in our domain. Okay, so the critical point is 1 with root 2, and the function value of 1 with root 2, our function is xy squared, so we're going to get 1 times root 2 all squared, which is 2. Okay, I'm going to go along. Here's one of my critical points, the value. Then I have my endpoints. So I have 0 as a value. I got no critical points in my interior. My boundaries, I got 1 critical point. It is 2. 2 is bigger than 0. So now I can go to my fourth step. We're going to state the extrema, we have the absolute max is f of 1 root with root 2 is equal to 2. And then we have the absolute min was a three-way tie, and it was f of 0, 0, which is equal to f of 0 root 3, which is equal to f of root 3 comma 0, and all of those are equal to 0. And those are our final answers for this problem. Okay, so the steps were exactly the same as the previous problem. The only difference is that it's a different function and the domain is slightly different. And so that's what you're going to see throughout, right? If you follow the exact same process, you are bound to get where you need to go in order to come up with your absolute mins and maxes. All right, one more problem. This is a word problem for absolute extrema. And we are asked to find the shortest distance from a point, 1, 0, negative 2, to the plane x plus 2y plus z is equal to 4. Okay. So we have a plane, and then we have a point. Okay, so this is a plane, and this is a point. And we want to know the shortest distance to the plane from the point. Okay? So it's just a visual of it. That's probably not what my plane looks like or where my point is in space, but that's just giving us a picture of what we're looking at. Okay, so what we can do is we are going to let x, y, z be any point on the plane. Then the distance between x, y, z and 1, 0, negative 2 is, well, we'll just use our distance formula. It's going to be the square root of, in parentheses, x minus 1 all squared, plus, in parentheses, y minus 0 all squared, plus, in parentheses, z minus a negative, so it'll be plus 2 all squared. Okay. Now, I need to somehow make it so my plane is taken into account. Okay. Right now, this is just like with x, y, z written the way it is, that's just like any old point in space. Okay. I need to somehow incorporate the plane into this distance formula. So I'm going to write that. Need to incorporate z into, or sorry, not z, the plane into the distance formula. And so it's easy to kind of stare at this and wonder for a while and never get anywhere. So I'll tell you what it is. What we do is we take the plane equation and solve for z. So take the plane equation, solve for z, and substitute this into the distance equation. So what that's also going to do is it's going to make it so we don't have x, y, and z. We just have x and y, which is kind of what we want because that's all that we've been working with. We haven't worked with 3 variables. That would make our problems so much more complicated if we had to deal with 4 dimensions. Okay, so we're going to deal with just the 3. So in the plane, when we solve for z, we get z is equal to 4 minus x minus 2y. Okay, so I'm going to substitute that in. And I get d is equal to the square root of x minus 1 all squared plus y squared plus, in parentheses, 4 minus x minus 2y plus 2 all squared. So I just replaced z with 4 minus x minus 2y. Okay, now I'm having another problem. I'm looking at this in the square root and I'm not wanting to take first partial derivatives. Like, that just looks horrible. So what we can use, and you're going to see this trick a lot in mathematics, you may have already seen it a few times before. So when d squared is minimized, so is d. So what I'm saying here is when the distance squared is minimized, so will the distance be minimized. So why not just, let's go ahead and let f of x, y, that's going to be our function we're working with, equal d squared. Then f of x, y is equal to x minus 1 all squared plus y squared plus, in parentheses, let me just simplify that to be 6 minus x minus 2y all squared. So this is what we're going to find extrema for. Or this is the, then this is what we optimize. Okay? So this is a positive function. Notice that f of x, y is a sum of squares, so there's no way to get a negative number from that. Also notice that, let me just write that real quick. So notice f equals a sum of squares and is positive everywhere. Also notice, so like if x was equal to 1 and y was equal to 0, we'd have really small values. But if we move x away from 1 and y away from 0 in either direction, so if we move x away from 1 and y away from 0 in either direction, f will get bigger and bigger because those first two terms will become bigger and bigger values. And so what that's telling me is that we have a function that has a minimum value. So f of x, y has a minimum value. All right, and now we're going to find it. So that was a lot of work right there. First, just setting up an equation that incorporates, like, what are we talking about, distance. Then going ahead and making sure that the constraint, the plane, like that's what we're working with, gets substituted in. And then realizing that working with distance is painful, so let's work with distance squared instead. Now, solve f sub x equals 0 and f sub y equals 0 simultaneously. So f sub x is going to be 2 times x minus 1 plus 0 plus 2 times 6 minus x minus 2y times negative 1. That becomes 2x minus 2 minus 12 plus 2x plus 4y. Let me just simplify that a bit. We have 4x plus 4y minus 12, and we're setting that equal to 0. And f sub y is equal to, let's see, taking the derivative, I get 0 plus 2y plus 2 times 6 minus x minus 2y times another negative 2. So this simplifies to be 2y. That'll be 12 minus 24. That'll be minus 2x plus 4x. That'll be minus 4 plus 8y. And so that simplifies to be 4x plus 10y minus 24, and we want that set equal to 0. Okay? So we have a system of equations to solve. We have 1 and 2. And we can use, they're linear systems, so we can use substitution or elimination. This one may be a little easier to use elimination. So if I do the first equation plus negative 1 times the second equation, then what I'm looking at here is 4x plus 4y minus 12 equals 0, and minus 4x minus 10y plus 24 is equal to 0. I add these two equations to get negative 6y plus 12 is 0, so y will equal 2. That's not right. Where did I go wrong? I know where I went wrong. Up here, this was not minus 12, this is minus 14. So right here, it's minus 14, which means right here, this is positive 10, which means right here, we get 10 over 6, which is 2 goes into each one of those. Let's see, 5 over 3. Okay, y is equal to 5/3. All right. Now, if I substitute this back in to this equation to solve for y, what I have is, to solve for x. What I have is 4x plus 10 times 5/3 minus 24 is equal to 0. Okay. When I solve that, work it all the way through, let's see, we've got x will be equal to 11 over 6. Okay, so my critical point, and I only got one, my critical point is the point 11 over 6 with 5/3. And then what I need to know is, like, is this really a minimum? Because, you know, I kind of talked about it in this little notice statement in blue up above, but, you know, you might not believe me. So what I could look at is I know I want a minimum. That means I need my second derivative test, and big D should be positive, and f sub x should be positive, okay? So if I was to calculate big D really quick, big D of xy is f sub xx times f sub yy minus f sub xy times f sub yx. I go to my first partials to take second partials. So f sub xx is 4. F sub yy, it looks like, is 10. F sub xy is 4. And f sub yx is 4. This is going to be 40 minus 16, which is 24, and that's positive. And f sub xx was 4, which is positive, and those are true for all xy values. So therefore, f of 11 over 6 with 5 over 3 is, I should say, I don't want to do that quite yet. Hold on. Therefore, the point 11 over 6 and 5 over 3 gives a minimum distance. Okay, now the reason I changed how I was wording that is that if we go back upstairs to read what the question was, it says find the shortest distance. So it's not asking me what f of xy is. It's asking me what is little d. That means I got to plop everything into that square root function, okay? So the shortest distance is little d, which is the square root of, in parentheses, 11 over 6 minus 1 all squared, plus 5 over 3 all squared, plus 6 minus 11 over 6 minus 2 times 5/3 all squared. I just popped this into my calculator. I have got a great TI-30 or TI-36S. They both will simplify and give me an exact answer of 5 square root 6 over 6. Okay, that is the shortest distance between the plane and the point that I was given. All right, so you've seen a couple of different boundary problems for absolute extrema. We've done one of the application problems. Hopefully those will be good for helping you out in the homework. Definitely read through the book. There are lots of great examples in there as well. And then reach out if you have any questions.